Welcome to AI for Good, the leading action-oriented, global and inclusive United Nations platform on AI. Organized by ITU, in partnership with 40 UN sister organizations, and co-convened with Switzerland. The goal of AI for Good is to identify practical applications of AI to advance the United Nations Sustainable Development Goals and scale those solutions for global impact. In today's session, we're counting on you to use the live video wall feature to ask questions and post comments to help create an engaging discussion. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished panelists and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor is yours.
Welcome to today's AI for Manufacturing webinar. My name is Li-Hui Wang. I'm a professor of KTH, Royal Institute of Technology, located in Stockholm, Sweden. I'm also the curator and the moderator of this webinar series on AI for manufacturing. Today's topic of the keynote is an AI pathway towards sustainable manufacturing. We are fortunate to have Professor Robert Gao with us today. Let me briefly introduce the CV of Professor Gao. Professor Gao is a KD Steady Professor of Engineering and Department Chair of Mechanical and Aerospace Engineering at Case Western Reserve University in Cleveland, Ohio, USA. Since receiving his PhD degree from the Technical University of Berlin, Germany in 1991, he has been working on signal transduction mechanism for sensor design, stochastic modeling, and AI-based data analytics for improving the observability of a dynamic system, such as manufacturing machines, with the goal to improve process and product quality control. Professor Gao is a fellow of the American Society of Mechanical Engineers, ASME, Society of Manufacturing Engineers, SME, Institute of Electrical Electronic Engineers, IEEE, and International Academy for Production Engineering, CIRP. He has published more than 400 technical papers, including over 190 journal articles, 3 books, and holds 13 patents. He is a recipient of SME Eddie Whitney Productivity Award, ASME Blackout Machine Tools and Gauge Award, IEEE Instrumentation and Measurement Society's Technical Award, IEEE Best Application in Instrumentation and Measurement Award, and SME Career Award. He is the chair of a collaborative working group of AI in manufacturing, CWG AI of CIRP, and the chair of the scientific committee of a North American Manufacturing Research Institution, NAMRI of SME. Currently, he is serving as a senior editor for the IEEE ASME transactions on mechatronics. Ladies and gentlemen, please join me in welcoming Professor Robert Gao to the virtual podium. Professor Gao, the floor is yours.
Thank you very much, Professor Wang, for your very kind introduction. Good morning, good afternoon, good evening, everyone. Dear audience, wherever you are in the world, it is my distinct pleasure to be here today and to share with you some of our thoughts, work that have been done by my research collaborators, postdocs, students, and myself in the area of AI, and share with you our views about how AI can do good, which is the main topic of today's presentation. So in the following 45 minutes, I would like to share with you some concrete thoughts and results of our work. So now I'm going to share my screen and to start the presentation. Thank you. Okay, I hope everyone can see my screen. Is everything okay?
Yes.
Okay.
Yeah.
Thank you. So the topic of the title of my presentation today is an AI pathway towards sustainable manufacturing. Again, my name is Robert Gao. I'm with Case Western Reserve University in Cleveland, Ohio, USA. So in today's presentation, I'm going to first go over a couple of general concepts, starting with the question or the answer to this question, namely, what is good? And our understanding of good, we wanted to use the UN's Sustainable Development Goals, SDGs, to motivate this conversation or this presentation. I'm going to go briefly over the concept of AI and what is the possible, from our perspective, impacts of AI on the SDGs. After that, I'll be talking about some specific examples of AI for good in the area of manufacturing, specifically sustainable manufacturing and SDGs. And I'll be touching upon the so-called AI integrated digital twin for sustainability and illustrate the impact using 3 case studies as listed here, and then to draw some conclusions. First, what is good? Well, good, as defined by the United Nations Sustainable Development Goals, or SDGs, is illustrated here in the 17 goals, and they cover a broad area. If you can see my mouth here moving, from the area of no poverty, gender equality, to reduce the inequalities, improve life on land and life below water. So these are great goals that is defined as good. And the question is, how do we achieve this? And with the help of AI. So specifically, our thought is that we would need to identify some practical applications of these AIs to advance the SDGs and scale solutions for global impact. To begin, what is the AI that we are talking about today, or as in the meeting? There are various definitions, and the one that we're going to use today is the one that is given by Andrew Moore back in 2014. Namely, AI is the science and engineering of making computers behave in ways that until recently we thought require human intelligence. As we have seen in various media reports, scientific articles, as is shown here in Nature, Advanced Materials in Science, AI has been reported to do a lot of very interesting things, from playing professional goals, as illustrated here, to helping optimize nanomedicine design or predict protein structures. So one example here is how AI has learned to play this goal, as is shown here. So specifically, there are a lot of details that I will not be able to go into, but if you are interested, certainly there are many articles and reports about this. So basically, in terms of using AI to learn to play Go, 2 neural networks, as illustrated here, have been built. One is called a policy network, the other one is a value network. So they together will determine the so-called probability or likelihood of every move, and then which is defined as policy, and the goodness of the move, or the goodness of what is the current state defined as a value. So basically what happened is that in the so-called self-play of the game, each move made by the AI algorithm will be evaluated using the so-called Monte Carlo tree searches, MCTS. So basically, if we look at this chart here, there's a state 1, state 2, and so on until the game is over. So for each move, for example, we have a black stone here, then the system or the algorithm will evaluate where to put the white stone, right? There are different opportunities, possibilities like above it, below it, to the left, to the right, and so on. So each move will be evaluated and then certainly recorded. So through this repeated recursive process, the algorithm will learn and basically then become more knowledgeable and more mature. So that will lead to the completion or the training of the network, and then through this learning process. So as a result, what we have seen, we've heard is that in March 2016, there's this play between this AI algorithm and a world champion, as is illustrated here. So the person on the left is executing what the Go algorithm, is telling him to do, because the execution of that algorithm will have to be done by a human being who plays the stones, white or black. But the result is very interesting, obviously. So in terms of AI for achieving the overall SDGs, there are reports showing that they're altogether almost like 71% of the targets across all the 70 SDGs based on peer-reviewed literature. On the left is what we call a flower chart, so to speak, and we see these 17 SDGs grouped in terms of societal impact, impact on economy, and impact on the environment. This yellow, blue, and green. So we see that AI has impact on nearly all of the SDGs, whether it's a societal, economical, or environmental. So this is an illustration, very evident to show the potential impact. Granted that not all the anticipated benefit or impact has been achieved, but from these numbers, without parentheses and with meaning that this is reported in the peer-reviewed articles, literature, we can get a very clear picture of what AI can do. So there are also examples of how AI has helped to tackle a number of problems, big problems. For example, in this article published on the Journal of Science, the title being Combining Satellite Imagery and Machine Learning to Predict Poverty. So a group of researchers at Stanford, they did something very interesting, and they try to understand how to tackle poverty, and by using imagery from the satellites. So what they did is to use a so-called deep transfer learning to analyze publicly available satellite images for poverty prediction. So the solution, of using AI, the idea was motivated by the fact that if we were to do, for example, survey can be very expensive to execute, typically costing almost like $500,000 to $1.5 million each of them to perform. And if we do, also surveys are typically not participated, by household. And generally, that rate has been low, as is illustrated here. So, but understanding the poverty distribution is important because it affects immediately or impacts policymaking of a country. So what they did was to take images from satellites during the day and during the evening, and use this basically to train a neural network, and the convolutional neural network in particular. And So basically using transfer learning, so they can train this network and to predict from what they have seen from the daily during the daytime images to predict what the nighttime light intensity should look like, and then compare with nighttime images, and then the system can learn from the images and say and make a judgment about the poverty state, which is quite remarkable. So this the accuracy of asset prediction has been up to 75%. Very interesting and significant. AI has also been reported success in fighting COVID, as is reported in this Nature Medicine. And they use federated learning for predicting clinical outcomes in patients with COVID-19. And obviously, as we all know, COVID-19 has caused a worldwide healthcare crisis just in recent years. And medical resources, as a result, has been overwhelmed, stressed very thin. So the challenge is that from each of the hospitals is listed here, so each of them, has been had worked on developing so-called models to predict, based on the patient's information, what kind of, for example, ventilators will be needed, and oxygen needs to be predicted in order to have the machines available. And the problem is that if we rely on each of the hospitals to do its own, the prediction result, the model's reliability and accuracy cannot understandably be very high, because you have only limited data to train the neural network. So ideally, you want to have a very powerful, good model that has incorporated data from many, many hospitals. However, there's an issue, limitation, namely patients' privacy concerns. There's a laws that prevent the sharing of patients' privacy information. So what this federated learning algorithm method has been able to do is to enable collaborative global modeling of the oxygen needs without each of the hospitals sharing specific patients' data, but only some so-called weights, the weights of their models and neural network. So by sharing only the weights or the trend of the weights development going up or down, this so-called federated server, which represent a model, a global model, can be built, and then that provides much better accuracy and reliability in predicting the oxygen needs. And it is reported that using federated learning, 92% could be achieved, whereas with non-federated learning, only less than 80%. So the difference is quite clear based on the information related to 20 hospitals. Okay, last but not least, AI has been able to improve manufacturing. This is a study that my group has done and publishes its CRP annals a couple of years ago, where we reported how deep learning-based technique has been able to more accurately predict the so-called material removal rate in semiconductor wafer polishing. And obviously, this material removal rate prediction is important because it impacts directly the productivity of semiconductor chip manufacturing. But the process has been very complex, as is illustrated in this figure on the bottom right. And there's this is ultimately a so-called mechanical and chemical polishing process that involves, for example, pressure applied by the pad and to the wafer. And besides pressure, there's also the hardness, the film type, wafer size. And because it's a chemical process, there's also the slurry type, abrasive size, pH values, and so on. So to incorporate everything into a physical model, that has been historically challenging. So we use the deep learning technique for MRR prediction and the result has been very encouraging. So comparing to two popular physical models, if we use this prediction error as a measure, so we were able to reduce the error from, for example, 29.5, and that is predicted by one model, another model 77.5, our error was on 2.7. So that illustrates the power of AI. So in the next, I'm going to talk about some further specifics of AI for good in manufacturing. And the reason why I chose this topic for presentation today, using manufacturing as the driver, is because of its critical importance of manufacturing in two various important areas. To begin with, the importance to economy. And manufacturing has been the largest non-service sector by simply the number of workers, according to a survey in 2021. Specifically, the report was that there are over 14 million workers employed in the area of manufacturing, and that accounts for nearly 10% of the total labor force in the US, as we see here. There are some other areas that have a larger portion, but they are basically service related. And what we're talking about is non-service sector. So manufacturing, although having only about 10% of the labor force, has contributed in a way that has created outsized economic impact. Again, from these numbers on the right, for example, 60% of exports, 70% of R&D spending, 35% of productive growth, and so on. They're all from manufacturing. So this contribution certainly directly relates to the SDGs in terms of well-being and economic growth, as illustrated by the goal number 3 and 8 of the 18 goals. Manufacturing is also critical to energy because it has a large share in terms of a greenhouse gas emission. Again, according to a study released in 2020. Specifically, there are some numbers in terms of the metric tons emitted in terms of the 1 billion as a unit. Manufacturing has produced this much of greenhouse gas equivalent, and about nearly 24% of the total greenhouse gas emission in the US was attributed to manufacturing. And also, manufacturing consumes a large amount of energy, as illustrated here, according to a study released in 2021. So about 26%, 27% of the total energy consumption in the US, again, is attributed by the to the manufacturing. So improving manufacturing certainly has a critical immediate impact on the SDGs, areas 7, 9, and 13. And then furthermore, manufacturing is very critical to impact to the impact on environment. For example, because of the waste production, during the production of the products and after life, so to speak, after product has been produced in its usage throughout the entire life cycle, as we see here, production related waste management, and we see this in various areas like value added, disposal of other releases and treatment and so on. We see these generally have been going up. And there's also so-called municipal solid waste management over this period of many years, over 50 years. So we see this increase. So again, considering this importance, improving manufacturing would have immediate impact or direct impact on sustainability. So now talking about the sustainability, again, the topic of today's presentation is a pathway. We're trying to find an AI pathway towards making good towards sustainable manufacturing. And sustainable manufacturing is defined as a way of creation of manufactured products through economically sound processes that can basically minimize negative environmental impacts, conserving energy and natural resources, and enhancing employee, community, and product safety. So there's a people, human, in the loop, front and center, and a community where they live, and ultimately the product. So here we see, again, the potential impact of sustainable manufacturing on the national economy, on the society, on the environment through the various aspects. So ultimately, sustainability is permeated throughout the entire life cycle of the product, from the design to material selection, manufacturing processes, the way the product is built, fabricated, manufactured, and then how it is inspected to ensure quality, and how it is used after it's been manufactured. And at the end of its life cycle, we're talking about the end of service life, for example, to recover the material, recycle the material, or use this to redesign, to better reduce the material usage, energy usage, and so on, so-called 6 Rs that have been discussed extensively in the literature of manufacturing. So for that purpose, one useful tool is so-called a digital twin, and that provides a platform for realizing sustainable manufacturing. And digital twin actually is a very interesting story related to this, that this was first introduced almost like over a decade ago, initially by NASA, when they worked on improving the physical model simulation of the spacecrafts. So as we can imagine, when you wanted to build an environment, a platform where you can digitally, in virtual, simulate the scenarios, the situations that a spacecraft is subject to, and then to simulate the proper actions and responses to those scenarios. So by definition, a digital twin, again, there are many of them. The one that I would like to use is introduced by IBM. It says that a digital twin is a virtual representation of a physical object or system across its entire life cycle, and by using real-time data to enable understanding, learning, and reasoning, as is illustrated here, a digital twin of a product, aerospace engine, or a production process. So there are several basic building blocks to construct a digital twin, where, as we see here, artificial intelligence play a critical role together with the sensors, sensing data, and the computational infrastructure and resource. There are literature about these various building blocks that you can refer to if interested. So I'm going to go into a couple of specific case studies of how AI can be good, play a great role towards realizing sustainable manufacturing. And 3 examples I'm going to give are the following: AI-driven design optimization, as illustrated here on the left. In the middle is AI-guided robotic waste sorting to replace human work. And last but not least, how AI has been applied to enhance manufacturing process sensing. First of all, AI-driven design optimization. So here we're talking about, in this particular paper that I would like to quote, refer to, is about machining metals to create the so-called blades for a product. And the process involves machining or metal cutting. And metal cutting, as we know, is a so-called subtractive subtractive manufacturing process. And although we hear a lot nowadays increasingly about additive manufacturing, subtractive manufacturing machining still account for a large predominant portion of industrial and commercial products. And therefore, different product designs, for example, geometry, dimension, and so on, that will drive the selection of the machining processes specifically. For example, how do you cut the metal using different process, turning, milling, and so on. And that would result in variations in the productivity measured by here as runtime. So different processes ultimately will lead to variations in real-world performance of the product. As illustrated here, we have an end milling versus a flank milling. End milling has a small area of contact between the tool and workpiece, but as a result, it's very flexible, and it can really manage and navigate, through this design profile and make it, produce a product as the designer has wished. Whereas in comparison, the flank milling process, it has a larger contact area, and as a result, it can cut faster than here. But faster comes possibly with some issues of a trade-off. The performance, namely, of the produced blade may or may not be as good as this one, right? So how to simultaneously consider productivity and product performance in terms of design optimization? That is an interesting problem to tackle. So here, AI can contribute basically through design optimization that takes care of these two issues, namely maximization in the manufacturing productivity, and at the same time, product performance. So that I'm going to illustrate in this comparison of end and flank milling, how this has compared with each other. So the specific example, as reported in this paper, is the design optimization of so-called impeller. Impeller is basically a rotor, as is shown here, and it's used to increase the pressure and flow of a fluid in a so-called turbo machinery, that class of machines. Either, for example, used as a centrifugal pump in the heating, ventilation, air conditioning systems, as is illustrated here, HVAC systems. So it increases the flow of the fluid as well as the pressure. So from here, input to this air outlet. Or in the jet engine compressor, here impeller is illustrated. So traditionally, or if we use a so-called end milling, we can create very much high degree of freedom and to create the contour, the profile, very accurately as designed. So the study has shown that following this approach, it will take about 122 minutes to produce this product, and it will ensure high pressure ratio and efficiency, as these are the so-called KPIs, key performance index. So the process goes like this. We have a impeller freedom freeform CAD model. Using the CAD model, the initial design, we do the manufacturing, create these blades as shown here for the impeller, and then we put it to aerodynamic testing to make sure that the result has the KPIs satisfying the design performance. And then the result basically, which is a measured performance, they can be sent back to this design, initial design. But typically, that is after the production. That is an offline action. And this feedback will add to the empirical knowledge-based geometric adjustment. With a digital twin, the question becomes, with the possibility with the increase AI availability, the question becomes, is it possible to optimize blade design to reduce manufacturing time? Obviously, 120 some minutes, 2 hours, that's too long, right? While minimizing performance loss. So how can we basically do faster but as good as using the this way of producing it? So there's reported the success in the so-called AI-enabled impeller design. So where the multi-objective optimization has been performed, which is supported by digital twin simulation of the machining process, as well as the performance testing. So the way it goes is that the researcher have converted from this free form to a rule-based surface, and in order to enable so-called flank milling, as is illustrated before a few slides ago. So here we're talking about the digital twin enabled this rule-based geometric conversion, so that I can use a different type of tool that is a larger contact area with the blade, but it cuts a lot faster. So we can do simulation in this virtual environment to see what is happening during the process, and also what is happening with the aerodynamic testing. And then we create this using flank milling. The message, the information will be sent back to basically the digital twin, and this is an iterative process. So here is what we see in terms of the impeller design optimization scenario. We have a digital twin on the left, and here we have the AI implemented by the so-called reinforcement learning. And the specific is that we have a so-called critic and actor. Basically, actor would evaluate, if we do this, what needs to be done, so to speak, for determining what geometry adjustment is needed, because we want to use a different tool and requires a different type of models that is based on rules. And then the reinforcement learning algorithm would evaluate how good is the conversion, is adjustment, and it will provide a so-called score. So this is illustrated a recursive process, and the score would tell the actor, yes, you are going in the right direction or not. And how good is the score? Actually, that comes from the so-called reward evaluation from the digital twin. So this is a process that is recursive, and this is what we see as a result of the process. So impeller design optimization, the result is that, again, here in the upper row, we have the traditional way of doing it, and we recorded an actual runtime or production time of about 2 hours, but with good results. Now we do it in a different manufacturing process instead of end milling, using flank milling, and we predicted the runtime by using the digital twin would be just under 10 minutes. However, there could be some pressure sacrifice or trade-off that we need to keep in mind. And once we started, having done all these simulations in digital twin, we start to produce it, and we found that instead of 9.8 minutes, it's a little longer, 10.2 minutes, but still, after all, this means comparing to the 100, over 2 hours, we had a significant reduction in the manufacturing time of about 91.6%. We have a trade-off of about 2% actual pressure ratio loss and efficiency loss. But all in all, this is a significant improvement enabled simply through this AI-enhanced design optimization. So details are reported in this paper published in 2021 in the Journal of Manufacturing Systems. The next case study I'm going to illustrate is so-called AI-guided robotic waste sorting. We all know that there's a lot of solid waste produced each year in the world, specifically in the US. There's this report saying that about 300 million tons of solid waste is produced or was produced in 2021. And sorting waste is typically done by human workers. As we can imagine, this environment work is unhealthy, and workers will have to stand there for long hours, and the environment is loud, dusty, and there are all kinds of materials. Many of them are toxic. And the productivity of sorting it also varies because of the fatigue, right? So ideally, it would be good to have AI assisted sorting using robot, as is seen here on the right. So that way we can reduce the workers' exposure to unhealthy environment and improve sorting productivity at the same time. That would be something that we would love to see. So in order to realize the so-called robotic waste sorting, we need a couple of elements like vision system, a robot, and computational infrastructure. So first thing involved is object detection. We have to see the robot will have to know what is the object that is going to detect and to sort, and then that needs to be put into action. So this was done by using the so-called convolutional neural network. Details I will not go into, but this gives us an idea that what the network does is to recognize the low-level image features, for example, edges and lines, and that will be assembled into a high-level information, like the relationship between the objects. And then in order to guide the pick and place, so to speak, of this solid waste. So basically, a two-step operation. One is the object identification, the other one is the localization in order to pick and place. So this has been implemented in 2 US-based facilities in Colorado and Michigan, according to the literature. And AI was able to do a good job. For example, 60% increase in productivity, specifically translated into minute, how many picks per minute has gone up from 50 to 80. And there's an 11% also increase in the recyclable capture rate. So this is great. And the question then becomes, how can we do better? Can we do better? And because there's a space, a room for us to improve, and we want to further increase the accuracy. And the issue is this: we can use a digital twin to realize that. And using digital twin means that we have to create an environment that is authentic, realistic enough for the robot to learn. And that is done again by AI, and specifically a so-called psychogenerative adversarial network, or PsychoGAN, has been developed to transform the simulated images, as is shown here, that is not so realistic, to train a robot to something that is much real. And this is the result that we see in a digital twin environment. Again, the details are provided in the literature. So basically, the conclusion is that without this PsychoGAN based transformation, there's about 21% success rate, whereas with this transformation enabled by AI is 70%. The last case study I'm going to go through quickly is AI-enhanced process sensing. And this was a work that my group has done in collaboration with the Professor Dave Kasmer's group at the University of Massachusetts Lowell. So basically, we were looking at a way to better understand what is happening within the so-called cavity of injection molding machine, which is used to produce plastic products, as illustrated here. And the reality is that injection molded products, plastic product, makes up about 30% of all the plastic products worldwide. So therefore, effective monitoring and prediction of the quality is important. and that has to deal with what is happening in this hot, high pressure and enclosed, mechanically, hermetically and technically enclosed environment. So, and specifically, there are 4 parameters that affect immediately the quality of the injection molded products, namely the melt pressure inside of this cavity, the temperature, the speed at which, or the velocity at which the melt flow flows into this cavity. We know more about what is happening inside of this injection mold machine, then the more we know, the better quality control we can enable. If we know 4 of them, we can have up to 92.5% expectation of the measurement of the quality prediction. So here we show a multivariate sensor that we have developed that enables the prediction or measurement of all 4 parameters from within only one sensor package. And the sensor package looks like the one shown on the upper left. Basically, we call it a multivariate sensor that is able to quantify all 4 parameters from one sensor package. And we compare this performance with 4 commercial sensors, CS, as illustrated here. Our sensor is a so-called multivariate sensor, MVS. So the 4 commercial sensors, each of them can measure only one parameter, namely either temperature or pressure. They were placed at different locations of this injection mold path, so to speak. Within the cavity is here. It's a workpiece that is going to be molded. So the comparison result is very encouraging, as we see here. And this is a 45-degree lines with the horizontal axis showing the observed or measured part thickness, and the vertical axis is the produced or predicted. So if everything that we predicted is exactly what was measured, then this point data would be right on this 45-degree lines. As we can see, we have a much higher location, percentage of location of the yellow dots along this 45-degree lines than the blue ones. The yellow ones represent our MVS multivariate sensors, whereas the blue ones are the commercial ones. So we have a over 90% success rate versus about 70–80%. This is for both the thickness and the width of the part. So very interestingly, we further look at what AI can do to tell us out of the 4 parameters, which one or which ones are the most important. So, and we did analysis using one of the techniques, and it's a so-called kernel particle partial least square, which is an extension of the PCA technique, and that is one of the unsupervised learning method. And this KPLS basically can relate the influence, the importance of the parameters with ultimately the geometrical accuracy of the part or part quality, which is a supervised learning method. So as we can see, the method was able to tell us that actually velocity has the highest correlation with the part geometrical accuracy. Everywhere we see the Vx, we have a higher accuracy. And we see that graphically that the velocity measurement is very much aligned along this part or with the part quality illustrated here. Whereas others, there seems to be a high level of cross correlation, for example, between the temperature and the pressure, but they are in a different direction. So basically, in conclusion, we found that the rapid advancement of artificial intelligence has transformed the landscape of realizing UN's Sustainable Development Goals, SDGs, from tackling poverty to fighting COVID-19, to sustainable manufacturing. As an industry section of high significance importance to national economy, workforce development, and energy or material consumptions, manufacturing is increasingly embracing sustainability and using AI to contribute to SDGs. We think that the integration of AI with digital twin has shown to advance the state of the art in design optimization, process sensing, automated recycling, and so on, ultimately leading to improved productivity, material and energy efficiency, and end-of-life service. And realizing true sustainability in manufacturing will require not only deeper integration of AI with physical domain knowledge, but also coordinated efforts in raising the awareness about sustainability by both academia and industry. I would like to take this opportunity to acknowledge support from the National Science Foundation in the US. Over the years, decades, over 20 awards from grants from NSF, and we greatly appreciate and thank the support from the funding agency. Our work has been supported by the manufacturing industry. For example, injection molding, sensing research we had a collaboration with these companies. And I would like to thank my colleagues, collaborators, and former student and current postdoc, Professor Dave Kasmer, Professor Joyan Fan, Peng Wang, and Dr. Jianjing Zhang, currently with me here at Case Western Reserve University, who has contributed substantially to the creation of this presentation. And last but not least, I want to thank you for your careful listening. Thank you very much.
Thank you, Robert. Very impressive and a rich presentation. So in today's keynote talk, Professor Gao introduced first from the AI definition and through a number of different case studies, examples, how they contributed to the UN 17 SDG goals. So this is a very comprehensive. The second half of the presentation specifically focus on the manufacturing domain, from design optimization to waste sorting, all the way to process improvement optimization. So I would encourage you to use this opportunity to raise your questions and discuss further with Professor Gao. While you are preparing or typing your questions, perhaps I can ask the first question. Robert, you mentioned a number of different ways to use AI models to solve practical manufacturing problems. Many of the AI models or deep learning model, reinforcement learning models, they are very task-oriented. So in that sense, the model are tailored or trained for specific problems. Once it needs to be applied to a different problem, even so, we can use transfer learning, still need some training to make the model to reach a high accuracy. In your opinion, is it possible to have a more general purpose model that can be trained once and used for different problems to save the time-consuming tasks from the users? What's your view?
Thank you very much, Professor Wang. This is an excellent question, and it is one of the key issues that people have been working on, trying to find an answer. And my view is that in general, certainly, and at the end, I would say for each specific problem in the real world, there will be specific optimized solutions. So just like in order for to provide the best solution, best answer, that in order to measure something that is physical, for example, let's say temperature, and there are different ways to measure temperature. right? There's a direct or indirect ways to measure temperature. And therefore, there are different temperature sensors. So which sensor to use, certainly, it depends on the application. It depends on the constraint, space, temperature, humidity, and so on. So I would say this thought on generalizable AI, that will continue to exist, number one. Number two, however, there will be, and there has been reported studies on how to possibly make an AI solution more general. And you mentioned transfer learning, and there's physics-informed, data-driven learning, few-shot learning, and so on. And but ultimately, I think the question can be answered from two perspectives. One is the so-called model-based. I would like to use that, approach, model-based AI and data-driven AI. I would say model-based, we know it follows a model, and basically there are some predefined rules. For example, if this happens, then do this. If that happens, then do that, right? So just like F equals ma, right? And that is a physics-based solution. So that is widely applicable to many of the real-world problems. So if we consider from the perspective of a rule-based AI, then I would say this category of AIs can be very well generalized across the different tasks. But of course, the rule-based AI also have its techniques also have their limitations. So I don't think there's a clear-cut way of saying that if we use fuzzy logic, for example, or use some other related models, then it will be able to solve all the problems in the world. It will not. But that is a possible way of doing it. In terms of data-driven AI, I think there are discussions, for example, on whether we can build my data-driven AI algorithm in a modular way, different modules, right? Combined together, it becomes a good AI algorithm. But then maybe I can swap out a few of them and then to address specific problems. And that way, at least I have a more generalized platform or core of AI, algorithm. And then that can be modified, adapted to specific problems by using some customized specific apps. And that, I think, is, I would say, that's a possible thought pathways towards generalizable AI.
Thank you. Yeah. Now we have one question came in. The question is from Reinhardt School. Question for Robert Gao. Where might manufacturing be 5 or 10 years from now?
Very good question. And I don't have a crystal ball, but I think the general trend, as I observed, is that everything in manufacturing will become smarter. That's why we use the term smart manufacturing. And we have some studies ourselves, also in collaboration with Professor Wang's group, on smart factories of the future. And that in that study, we said that we're going to use leverage the benefit of so-called big data. So my short answer to the question is that in 5 years, I would envision a higher percentage of AI adoption on the factory floor, and that will increase the level of autonomy or automation, but with human in the loop, because ultimately all these clever techniques and so on, clever machines, smarter machines, human ultimately make the final judgment and final say. So AI can make some suggestions, recommendations, but human basically ultimately makes a decision, and it's human that creates those technology. So I would say in 5 years, I'm hoping to see smarter machines, smarter processes, because of the ubiquitous, more widespread installation of all kinds of sensors, sensing modality, data, and in terms of time series, in terms of images, text, words, voices, and so on, and congregated, integrated together, then it provides a higher level of intelligence to make manufacturing more energy efficient, more material efficient, and with higher productivity. I hope that answers your question.
Thank you. So the next question is from Jin Cui. Thank you for the great presentation, Professor Gao. What do you think of the relationship between AI and digital twin? Thanks.
Very interesting question. I think digital twin is it grows out of a so-called CAD model, I would say, that's my understanding. So namely, to produce something, we need to have a first computer-aided design model created by, back to my time when I was a student in the 80s, there's a so-called AutoCAD, and later on there are many more clever smart products. But ultimately we have a CAD model, and the path from, or the jump, the bridge from CAD model to a digital twin, as we call it, as we understand it, is that a CAD model is a static entity. It's a model based on the designer's thought, idea, vision, whereas a digital twin is something that provides an entire comprehensive digital environment in which I can simulate what is happening with my product. Once it is manufactured, built, once it is used, and then that living entity, I would say, living model, can be updated by what I measure during the actual production, actual performance, usage of the product. So what role does AI play here? I think AI plays the role of making the digital twin lively, updatable, refinable, and ultimately executable to impact the performance of the product. In an example of impeller design, I showed a digital twin by a research group, and they built a digital twin to first simulate what would happen with this flank milling, and they predicted a much shorter, much quicker production. And then they found that the production, although not as short, instead of a 9.8 minute, it took the process 10.2 minutes. But after all, that means still nearly 92% of the productivity improvement. And that knowledge is important for any shop managers, right, before the product's made. And more importantly, because the digital twin can be updated by the actual measurement from the sensor, or various sensors. So the next round of prediction, the digital twin will give more accurate prediction, and that would immediately impact the shop floor in terms of the scheduling, the planning of the manufacturing process. So I would say in that particular example, AI was very helpful through the so-called reinforcement learning. So that is the AI's contribution, namely to make digital twin a reality, a living, a lively, and refinable, updatable model as compared to the traditional CAD model.
Yeah, because of time, let me ask the final question. Talking about the digital twin models, the digital twin model can be created in very detailed, fine-grained model. And this may take some time to do the computation, no matter which AI algorithm you use to calculate, it takes computational power and time. Or it is possible to create a coarse-grained model, eliminate some details, and this can speed up. So there's two extremes of model. One is very detailed, another one is a coarse model. But the computational efficiency and the speed is quite different. In that situation, for the first-time user, how should we choose the level of granularity to build a model?
Very good and highly relevant question. I think we have to ultimately, and this is AI, any AI application research, ultimately it needs to do good in real world. So I think what we need is a so-called adaptive AI, right? That can help us, provide us with a choice of decisions in a coarse versus fine models. For example, I can imagine that in parallel or similar work, that involves both the manufacturing and aerodynamic testing. So we can have a coarse model to begin with, and that gives us some quick results. And then after that, I can, run CFD and so on to refine it, or we can run a few coarse, computational fluid dynamics simulation. That typically takes a long time. I run a few, get some basic result, and I put results into AI and let the network solve it. But at least the network will not be just initialized randomly, but with input from the CFD calculation. So that way we can combine the advantage of a very fine science physics-based simulation with this data-driven simulation by neural network. I think we have the choice there, and obviously the choice will have to come from human being who are, knowledgeable about this. But to answer your question, Professor Wang, I think this coarse versus a fine AI models, we need adaptivity of the AI, and we need to combine physics with data-driven things to reach an optimized solution. But I think that's a research direction to go, and people are working on it.
Thank you. We have one more question came in, so we can use the coffee time to further discuss this. So the next question is from Mason Fox. Do you think these tools have a potential for predictive maintenance to minimize the downtime on systems? What are the current limitations to deploying smart manufacturing in modern plants?
The answer is definitely, I think AI will be able, can indeed impact quality assurance, maintenance, and so on. And simply by more reliable and accurate prediction of which machine possibly is at which stage of its service, life stage, according to measured against the original design. And I think the benefit, based on our study here, research, talking to industry collaborators, big or small, people realize that. And for example, I've talked to some, plating companies here, and that uses exclusively, motors to basically transport parts from one place to another and dipping it, for example, the part into this bath with, chemicals, so to speak, for implementing realizing the coating, the plating. The problems, so they wanted to know when possibly my motor is going to fail, because if the motor fails, the motion will be stopped, right? You don't want this part being dipped into the plating bath, and all of a sudden the motor is, has quit. It cannot lift the part, move it away after a certain period of time. Then the part will become a waste, right? By staying in that place, at that place forever. The problem I see, I think I learned from conversations, discussion with the manufacturers, that there are two things. One is resource availability. Especially small and medium-sized enterprises, SMEs, they generally do not have dedicated personnel, IT people who are knowledgeable enough to do this kind of prediction modeling using AI and so on and so forth. So number one, so it is a resource issue. Number two, it comes down to the fundamental question is that, can I really trust AI? And how do I know? This seems to be a black box. Whatever it predicts. I mean, in academia, that's why you guys can write papers and so on and so forth, so do some, experiments in controlled environment. But on my factory floor, and this is a real world operation, I have to, make sure I'm staying, competitive, can benefit, have produced profit. So it's a trustworthiness of the AI technology that I think is ultimately at least one of the major bottlenecks to AI's widespread adoption. But I think on the other hand, from the research perspective, people have been working very hard on improving the so-called transparency and trustworthiness of AI. So I think recognizing, we understand there are so roadblocks and barriers and concerns, but eventually I think the adoption of AI, in particular for maintenance and so on, that will become better and higher, the rate of adoption. I think people work very hard on that, and a major roadblock that we need to overcome is the transparency and the trustworthiness. We need to know that just like F equals MA, it's not F equals a half MA or 3/4 of MA. And that is something that has to be proven, and specifically for my specific applications on the shop floor. But I think people are working on it, and I'm confident that we will reach that. We'll do better in the next 5 years. And going back to the previous question, what happens to manufacturing in 5 years? My vision is that it'll be smarter, it'll be more reliable, it'll be more economical. It's a long road. It's not just you say it, but I think with so many people working so hard on this, AI, as we all know, it has attracted such unprecedented level of interest from all sorts of all walks of life and in industry, commercial fields. So I'm confident we'll do better.
Yeah, Reinhard has a follow-up question for you. On which side of the debate are you? Will we need fewer or more people in the manufacturing sector in the future?
Very interesting. I think, manufacturing has gone, up and down through so-called, there's some here, at least in the US, there was in the past 20 years or so, outsource and becoming, less manufacturing oriented and more service oriented. But then the trend has reversed. Manufacturing ultimately, I think, has been recognized by, the government, actually everywhere in the world, that it is one of the pillars. So it will not go away. It cannot. No country can afford to have it manufacturing, fade and disappear and becomes 100% service-oriented country. So in that sense, I'm confident about manufacturing as one of the pillars for national economy. On the other hand, and there's the issue of distribution, of the workforce. So on which side am I? I think I honestly cannot predict there will be more manufacturing, workers, employees in the next 5 years or less. But one thing I can say that we're going through a phase of workforce development that we're trying to retrain, workers that belong to, who learned their skills in the previous decades, right? At the same time, we're producing engineers of the 21st century, at university everywhere, other universities, they're producing new engineers every year by tens of thousands, hundreds of thousands altogether. So, I mean, many of them will enter manufacturing. So in my department, in mechanical and aerospace engineering, the majority of our undergraduate, students will go into the industry. And there is clearly a need. So I'm not sure about the exact total number of employees in a factory. Did it go up or did it go down? But I would say we will have, certainly depending on the applications, the needs of the society and so on, and the number will be, I would say, stable more or less, and it probably would go even up because of the new demands, from machines. Although we have a higher degree of autonomy, there has to be a minimum number of workers, operators. But some of them may not be operating, exactly the machine. They may be shifting to other areas like maintenance, like planning, analysis that may or may not be considered as, in a traditional sense, as a manufacturing workforce. But I would say everything related is still part of a manufacturing. So maybe, and it's a long-winded answer. I hope conveys my thought. And although I cannot say for sure through a crystal ball that there'll be 150,000 more manufacturing workforce worldwide in the next 5 years. I unfortunately do not have that knowledge, but I think at least it'll be stable. I hope my prediction there is right. But there will be a shift, redistribution of the kind of work that people do in manufacturing.
Very good. Now we reach the time. And before we finish, let me introduce the next webinar. The next AI for manufacturing webinar, as you can see online, is already scheduled for January 23. This time will be at 9 a.m. Central European Time. Dr. Nonaka of Hitachi, Japan, will present the multiverse barrier-free, a new era for human-machine interaction for manufacturing. So please stay tuned. I would like to take this opportunity to thank Professor Robert Gao again for delivering a wonderful keynote, and also wanted to thank all the online participants, raise questions, and spend your time to listen to this very interesting keynote. So we will see each other next time. Stay tuned. Bye for now. Bye-bye.
Thank you. Bye-bye. Thank you, everyone. Have a great day. Thank you.
Thank you for participating in today's AI for Good session. We hope you've learned something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the eShop, and build your personalized AI for Good program. Let's shape the future of AI for Good.
Mm.